In this lecture, we will learn how to use the third-party model as a subcircuit in LTspice. During previous lectures, we explained how to include the third-party model like the spice model into LTspice using .model .model. This time, we will use .subckt .subcircuit to define the component by a collection of circuitry of intrinsic spice devices. The objective of this lecture are as follows. We want to import the third-party models using .subckt statement. We will learn how to use existing symbols, and another method is to create a new symbol. In addition, we would like to make the model portable among different PCs. Now let's begin. Let's start with an example to build a 5V Zener diode voltage regulator. Here are the design requirements for a 5V voltage regulator using Zener diode. The input voltage range is from 6V to 12V. The nominal output voltage is regulated at 5V plus minus 10% as tolerance. The load is 1 kΩ. The load current is 5 milliamps. Next, we will choose the Zener diode and the current limit resistor to complete this design. This is the schematic for the design. We have current limit resistor and we have a Zener diode to regulate the voltage at here. 1 kΩ is the load resistor. First, we choose to use a Zener diode with nominal voltage at 5.1V. The model number is MM3Z5V1. It is a 300 mW, 5.1 plus minus 5% Zener diode. The electrical characteristic is given in the table. The IV curve is shown here. The Zener diode is forward biased in the first quadrant, where the both voltage and current are positive. The current is flowing into the anode of the diode, and the voltage between the anode and the cathode is positive in the first quadrant. In our design, we want the Zener to operate in the third quadrant, where the voltage and the current are both negative. That means the current is flowing from the cathode to anode, and the voltage between cathode and anode is positive. When the Zener diode is reverse biased between 0 and the voltage at VR, it has some small reverse leakage current. Once the voltage is beyond the Zener voltage VZ, it breaks down and able to conduct high current, while maintains a similar VZ. Therefore, the Zener diode can clamp its terminal voltage within a very small range. So that's why it can regulate the output voltage. So electrical characteristics are shown here. This is the model number, and this is the Zener voltage, nominal 5.1V, and the minimal and maximum. This is the Zener current at IZT, which is the threshold at 5 milliamps. Other parameters are like Zener impedance, leakage current, temperature coefficient of VZ around the current at IZT, and the capacitance. So let's go to this link to get the basic information about this diode, and also we can go to this second link to get the library file from ON Semiconductors, which is a manufacturer for this diode. We open this library file in LTspice. So this is the subcircuit name, and we open the library file here. So this is the window to show the subcircuit syntax. So note that the subcircuit model is called MM3Z5V1T1. A very important information is the terminal Netlist order. So we can see the subcircuit followed by the name and followed by number 2 and number 1. number 2 and the number 1 are node names. Here, because number 2 shows up first, so this is the Netlist order number 1. This is Netlist order number 2. There are 2 terminals, and you can see the comments here. The anode is node number 2, cathode is node number 1. This subcircuit consists of quite a few different intrinsic models, such as diode and the resistors. So we need to choose a current limit resistor R limit. In our case, we want to calculate the value of the input current. The minimal input current is the Zener current plus the load current. The Zener current is approximately 5 milliamps. The load current is 5 volt over 1 kilo ohm is another 5 milliamps. The total current will be 10 milliamps. The current limit resistor is the minimal input current, the minimal input voltage minus V out divided by the I in, which is 100 ohm. The R limit must be less or equal to 100 ohm so that we can provide at least 10 milliamps. So this is the MATLAB Octave code to calculate the resistor value given a variation of input voltage from 6 volt to 12 volt. We can see that R limit is calculated according to different voltage at input. 100 ohm is corresponding to 6 volt as the minimal input voltage. So we need to use this 100 ohm. If we use 700 ohm, we cannot meet the current requirement for the low-end input voltage. Therefore, we need to use 100 ohm. Also, we calculate the power dissipation over Zener diode and the current limit resistor. The Zener diode power, the total output power for Zener is 5 milliamps times 5 volt, gives you about 25 milliwatt. And the current limit resistor power is I in squared times R limit. So in the worst case, at 12 volt, we can see the power dissipation over this resistor is about 70 milliwatt. From the datasheet, we know that thermal resistance of Zener is 416 degrees C per watt. Therefore, according to the power dissipation as 25 milliwatt, found that the temperature rise of the Zener is about 10 degrees C, which is acceptable. So there are 2 parts for a model. First, it has a symbol. It's like how it looks like. The second one is a library. So we use LTspice to link them together. The first method is we use the intrinsic device model. The first method is to use the existing symbol of Zener diode in LTspice. First, we copy and paste the subcircuit statement to LTspice as a spice directive. The important step is to include a diode model. We call it D. We press Ctrl and right-click over this Zener diode. We change the prefix to X, which represents a subcircuit. And then we change the value to the subcircuit model name. And we hit OK. In this case, we use the symbol as a Zener diode. Now let's open the symbol. We move the mouse over the terminals. We right-click, we can see the label name is a plus, and the Netlist order is number 1. We move the mouse over this terminal to see the label as minus, and the Netlist order is number 2. And also the labels are not visible because none is selected here. Again, I want to emphasize that the Netlist order really matters in this case. The plus terminal is the first node in the netlist. That is netlist order number 1. This one, the negative label, is netlist order number 2. Let's go back to the subcircuit model. So here, this one is the netlist order number 1. This one is the netlist order number 2, because this is the second appearance node in the netlist. Just to double check the polarity, in the subcircuit model, number 2 is the anode. That means the first appearance node is anode. The second appearance node is number 1, which is cathode. So go back to here, plus is anode, which is correct. And the minus is cathode, which matches with the subcircuit. I know this is a little bit confusing, but as long as the netlist order is correct, this model should work fine. Now let's hit OK, and as we said before, we input the subcircuit model as a spice directive. The hotkey is S, and we hit OK. This model is finished. We copy and paste the whole subcircuit as a spice directive here. Another method is just to use .include or .inc. We include the whole library from the local directory so that the schematic looks much cleaner. This is a transient simulation, shows input voltage and output voltage. The input voltage is changing from 0 volt to 12 volt and changes back. You can see the output voltage is well regulated around 5 volt, which meets our specifications. The second method is to build a subcircuit using a new symbol. Previously, we used an existing Zener diode symbol from the LTspice. So now we want to build a new symbol using subcircuit. So first step is to create a symbol. We open this library file in LTspice. We move the mouse over subcircuit and right-click. There is an option to create a symbol. We click that, and a window pops up to ask you if you want to build a symbol. Yes. Now the symbol is created. You go to the local folder called Documents, under LTspice, under lib, under sim, under auto-generated. So this one is the symbol we just created. We open this symbol in LTspice. We can see there are two terminals. This is a two-terminal device, number 1 and number 2. Again, this number 1 and number 2 is the label name. You can see number 1 corresponding to cathode, which is netlist order number 2. This node 2, as label 2, actually is netlist order number 1, which is anode. So this is anode and this is cathode. We can change their labels to make it more straightforward. So now we change netlist order number 2. Number 2 is 1, so it is cathode. We change it to K. And netlist order number 1, this first one, number 2 here, is anode. We change it to A, so that the labels are changed. So we know which one is anode and which one is cathode. This is very confusing, but once you know their netlist orders, you will get it right. Also, you can make it a diode shape if you like. I will skip this modification in this lecture. Another important step is to make it portable, so that it can be easier to share with others. We go to Edit, Attributes, Edit Attributes. We can see there's a model file. It's a long directory for this case, and after that it's gonna be the library name. So we delete the absolute directory on your local PC. We just leave the library name here, and we keep the same value as the model name, and we hit OK. By doing so, the model will search for the library in the local directory instead of the absolute directory, so that this file becomes portable. And we hit OK. Now we can copy and paste this subckt symbol into the same directory of the schematic file. Finally, you can find this .asy file, which is a symbol file in the simulation. We add a component and we change the top directory to the local directory. You can see the subckt symbol is here. So now the model becomes portable. If you hit OK, you can add this component as a subckt into your schematic. You can place the diode in the correct polarity. Now we can run the same transient simulation again. We put voltage probe over V in and V out. We can see this simulation gives the same result as the method number 1. There are two comments. The first comment is subckt model. The subckt model is useful for components with multiple pins when the generic model is not available. The second comment is to make this file portable, the entire LTspice files, including the library, the symbols .asy and the schematic.asc files, must be in the same directory. And you copy the whole folder to another PC, it can be run smoothly. Just to recap, in this lecture, we talk about how to import the subckt into LTspice. The first method is to use the intrinsic device model with existing symbols. So we change the model prefix to X as a subckt, and we change the value to the subckt name. The second method is to build a new symbol using the subckt, and then we can edit the attributes to make it portable. The subckt circuits built by two methods are both portable. Here are the good references for this lecture. Thank you very much. See you next time.